Alright, this video is about lab scenarios that involve stoichiometry. So a lot of times when they give you a lab scenario, obviously you're not actually going to do a lab on the AP exam, but a lot of times they'll give you a scenario where you're pretending that you've got data from a lab. So one of the things that you'll see quite a bit is something like this, where they take a reaction that they've put through a filter. So they'll have like a filter paper, and you dump that liquid in there, and then the liquid comes through here, and then the solid stays in here. So this is a solid, and then what they have to do is they have to dry it, okay? And they dry it one time, and then they dry it again, and then they dry it again. They usually dry it multiple times, and the reason that they dry it multiple times is to make sure that all of the water has been driven off. That's how they use it, is you want to make sure that all of that water is gone, okay? And so which of those three masses do you use? You use the very last one, or you use the one that is the lowest, okay? So whenever the mass should continue to drop as more and more of that water gets dried out and goes, is not part of that, the filter paper that's all wet will eventually be completely dry. So they will dry it multiple times, again, and that's to drive all of the water off. So why was the filter paper with AgCl dried 3 times? To drive all of the water off. Okay? And really, how many times should you dry it? However many it takes. If the mass keeps dropping, it means that there's still some water in there. So sometimes you may end up having to dry it 3 or 4 times just to make sure that all of that water is gone. So let's go back to the original problem then. So it says M plus is an unknown metal cation with a +1 charge. A student dissolves the chloride of the unknown metal, MCl, in enough water to make 100 milliliters of solution. They mix the solution with excess silver nitrate to cause AgCl to precipitate. So the equation would be MCl is going to react with AgNO3, and then it says it's going to cause AgCl. So this is a double replacement reaction where it's going to go AgCl, and that's a solid. And then MnO3 is going to be soluble. So the solid that's in here, is going to be the AgCl, and the MnO3 that's dissolved in the water is going to come through that filter, okay? Unless it's a solid, if it's dissolved in the water, it will pass through the filter. So, and again, once you rinse that out and make sure that only AgCl is in that filter, that's when you dry it and you make sure that all of that mass of AgCl here is correct. So, the student collects the precipitate by filtration, dries it, and records the data shown below. The molar mass of AgCl is 143. So they want to know, what is the identity of the metal chloride? So this MCl, what is that M in MCl? So first of all, we know that the mass of the filter paper plus that AgCl is 2.23. Okay, so again, don't try to think of how do I get to the answer. Think, what's a step that I can take here? Well, I know that if I know the mass of the precipitate plus the filter paper is 2.23 and the filter paper is 0.80, I could take 2.23 and subtract 0.80. And that would give me 1.43 grams of AgCl. Okay, and so now that's my mass of silver chloride. Well, again, think about the next step. Well, what do I do with grams? Well, 1.43 grams of AgCl. I don't know. I could convert that to moles. And remember, they told me the molar mass is 143. So 143 grams per mole of AgCl. And again, we have the balanced equation up here. They're all 1-to-1 ratios. So we could use stoichiometry and go, oh, well, 1 mole of AgCl was formed when, again, they're asking about MCl, right? What's the identity of the metal chloride? Okay. And you go, well, that's 1 mole of MCl is what it was called. And I can't go to grams, though, because I don't know the molar, I don't know what M is. It's some unknown element, so I have to stop there. So I'm going to take 1.43, I'm going to divide by 143, and that equals 0.01 moles of MCl. Okay, now I'm stuck again. Again, we're trying to find the identity of the metal chloride. The way you can identify a metal chloride is by its molar mass. Okay, well, I know the moles of MCl. Man, if I just knew the mass of MCl that I started with. Oh, hey, what do you know? You do. The mass of MCl is 0.74 grams. And so molar mass is 0.74 grams divided by 0.01 moles. Oh, look, grams over moles equals 74 grams per mole. No calculator needed there. Okay. Now, does that answer the question? No, it does not. Now I have to figure out which of these has a mass of around 74. Well, 23 plus 35 is 58. 39 plus 35, though, is 74. So, therefore, it is potassium chloride. Okay, another type of lab scenario involves what's called the analysis of hydrates. Okay, a hydrate is something like this, where you have a compound, like an ionic compound that has some water attached to it. And in this case, this would be called copper 2 sulfate pentahydrate. And of course, when you heat those up, what happens is that water will eventually boil off, and you'll just be left with what's called the anhydrous form of that, which would just be copper sulfate. Okay, so anhydrous copper 2 sulfate is just CuSO4, but now it just doesn't have the water attached to it. So, in order to determine the number of water molecules associated with this compound, we're basically gonna have to figure out, again, we're driving off all of the water. So to find the number of water molecules once the laboratory part is complete, what do? We determine the mass of the water driven off, basically by subtracting, just like how we did in the previous problem when we subtracted the filter paper from it. And then we convert that to moles. And then we use the mass of the anhydrous salt, the mass, again, at the end of the problem, once all the water's gone, and convert that to moles. And then basically we're just going to compare them. Okay? So, in part A, it says determine the value of X in the hydrate. So you have an 11.73 gram sample of the hydrated salt. It's heated, you drive off the water, and re-weighed multiple times. Again, why do you weigh multiple times? To make sure all the water's gone. Until you reach a constant mass of 6.410. So the first thing we can do is we can take 11.73 grams, and that's the mass with the water, and subtract 6.410, and that will get us the mass of whatever was driven off, which is the water. So 11.73 minus 6.410 equals 5.32 grams, and that's of water. And then the 6.410 is the mass of the COCl2. So we've got two masses here. We've got 5.32 grams of H2O, and we have COCl2, and we have 6.410 grams of that. Okay, so in this case, basically what we're doing is we're going to compare the moles of each of these to each other. So we have 18 grams in 1 mole of water. 5.32 divided by 18 equals 0.296 moles of H2O. And then for COCl2, we need the molar mass of it. So cobalt is 58.9 plus 35.5 times 2 equals really close to 130. We'll say 129.9 grams per mole. And 6.41 divided by that answer is 0.049 moles of COCl2. Now, what is the ratio of moles of COCl2 to moles of H2O? Well, we have to divide them. Okay, we're going to divide them basically by the smallest number. So similar to percent composition, when we're trying to find the empirical formula, very similar. The smallest number is 0.049. So there's 1 mole of COCl2 for every 0.296 divided by 0.049 equals 6 moles of H2O. Okay, So, therefore, the value of X in the hydrate is 6. And so the formula would be written COCl2 dot 6H2O. Okay, and then B, why is the hydrate heated and cooled multiple times? Again, we already talked about that. Again, to drive off all of the water. Okay, one more. So, again, another lab scenario here. It says a student investigates various properties of silver compounds in the lab. First, the student carries out the following procedure to determine the concentration of silver ions in a solution of AgNO3. The student adds an excess, we know what that means now, extra, right? 3 molar HCl to 100 milliliters of the solution, causing AgCl to precipitate. We kind of already saw one similar to this earlier. The precipitate is separated from the solution by filtering it through a pre-weighed piece of filter paper, similar to the previous problem. The precipitate and filter paper are rinsed with distilled water. And again, why do they rinse it with distilled water? Again, just to make sure there's none of that other product hanging around in there. You rinse it off with some distilled water, and then again, let it rinse, let it drain, and then dry it and dry it and dry it multiple times to make sure all that water is gone. So, part A says calculate the number of moles of AgCl that precipitated. The molar mass is 143. So this is not, the other one was more of a multiple choice type question. This is a free response. So we've got 3.578 grams of AgCl plus the filter paper. So obviously we need to subtract the filter paper. So 3.578 minus 0.718 equals 2.86 grams. And again, that's grams of AgCl. And then using 143 grams per mole, 2.86 divided by 143 equals 0.02 moles of AgCl. Okay, so that's how many moles of AgCl we have. Now, part B, assuming that all of the Ag plus ions precipitated, so that means all of the Ag that's here had to have come from the AgNO3. Calculate the original molarity of Ag plus in the solution before HCl was added. Well, if we have 0.02 moles of AgCl, 0.02 moles of AgCl, we can say that in 1 mole of AgCl, remember we did this with combustion analysis, there's 1 mole of Ag plus. Okay, and so we have 0.02 moles of Ag plus, and now we just need the volume. Again, they want the concentration, so we need moles of Ag plus, and then we need the volume of that solution. Okay, it says adds an excess of 3 molar HCl to 100 milliliters of the solution. So how much solution do we have? 100 milliliters, or 0.1 liters. So 0.2 divided by 0.1 is the same thing as timesing by 10. So that would be a 0.2 molar solution of Ag plus. Okay, and then part C, and then this will be our last question. The calculated concentration of Ag plus from the student's data is lower than the actual concentration of the solution. The student claims that the calculated concentration is too low because the filter paper and the AgCl precipitate were not fully dry. Do you agree or disagree? So if we go back and look at the data, if it was not fully dry, tell me about this number right there. Would that number be smaller, bigger, or the same? Well, if you hadn't dried it completely, then this number would be bigger. And so usually when they have a problem with this, I just kind of walk through the whole problem again. So if this number's bigger, then that number's going to be bigger. If that number's bigger, then our moles of AgCl are going to be bigger. And if your moles of AgCl are going to be bigger, yep, come back down to here, that number's bigger, which means your concentration is bigger than it's supposed to be. Okay, is that what happened? It says the calculated concentration of Ag plus from the student's data is lower than the actual concentration of the solution. Okay, so Do I agree or do I disagree? I disagree. Okay, and again, just kind of just explain why. Because a greater mass of filter paper and AgCl would produce a greater concentration. Okay, not a lower concentration. Okay, so hopefully you kind of see from this, don't try to solve the whole problem. Just think, what's one step I can do? Don't try to go from point A to point E in one step. Go from point A to, well, I guess I'll do this, to point B. And then from point B to point C, and then just don't worry about the whole process. Just do what you've been taught to do. Remember that these people know what you know. So they know that, even for me, they know that I can't go from point A right to point E without doing all those steps in the middle. Just do what you've been taught to do, and hopefully that will lead you down the path that will get you to that final answer here at the very end.